The region between the stress and the strain for a given material can be found experimentally. Let us take a spring and stretch it by applying a force, and this causes a change in the length of the spring, which is the change of the force applied, and note the change of the length of the spring. Regard the fractional change in the length, that is the strain, for the different values of force. The original length of the spring here is 2.5 cm. By plotting a graph between stress, which is equals to the applied force per unit area to the spring, and the strain produced is the change in the length of the spring, which is fractional change in the length of the spring. Spring is the strain. The curve here that we obtain helps us to understand how a given material deforms with increasing loads or force. So from the graph, we can see that from the region of O to A, the curve is linear. In this region, Hooke's law is obeyed, where stress and strain is directly proportional. That is when increase the force will increase the length of the spring. If I pull it, it will go over than 2.5, but if you remove the force, it will go back to its original length, which is 2.5. So from A to B, from A to B, stress and strain is not linearly proportional. In spite of that, the body returns to its original dimension when the force is removed. The point B in the curve is known as elastic limit, and point A is known as proportionality limit. If the force is increased further, the stress developed exceeds the elastic limit, like this. If you pull it with greater force, so in this region, the strain is increasing rapidly even for a small change in the stress. If I apply small force here, if you can see here, stress is a bit lower than point B. If you apply a small force, you also can change the strain value, because it is if you can see that it is represented by curve B to D. When the force is removed, say at some point C to D, the body does not regain its original dimension. You can see the length of the spring is longer than the original length. C is called yield point. At this point, there is a change of the internal structure of the material takes place, where the plane of the atoms of the spring slide across each other, resulting in a sudden increase in extension, and the material thins uniformly. But for this spring, you can't really see that it thins uniformly unless you give a greater force than I given. In this case, even the stress is 0, which is I'm not applying any force, but the length of the spring is not the same as before. So at this moment, from C to D, the spring is said to have a permanent deformation. This set of deformation is said to be plastic deformation. So point D in the graph is the maximum breaking stress of the material. At this point, additional strain is produced even by reduced value of force, which is you pull it more with extra force. Even you apply smaller force than before, fractures will occur at any point E. If you pull this spring with more force, it will break at some point. So, if you remember, from point C, the spring cannot regain its original length. So at this point, it will start somewhere at here, and I will put it as point T. So it is said that from region O to region B, this is we call as an elastic deformation region, because if you remove the force, the spring can go back to its original length. But starts from point C up until point E, here we call it as plastic deformation region. because the spring cannot regain its original length. It is permanently deformed and the length is not the same as the original length. Note that the graph is different for different types of metals, and this is a typical graph for ductile materials. So let me show you the difference between ductile material and brittle materials graph. I have a stress against strain graph for ductile and brittle material. Ductile materials shows elastic and plastic behavior, but brittle materials do not show plastic behavior.